Welcome. Today we tackle the last topic in our second unit here in physics, and that is free fall. Free fall, not just a ride at Great America, but it's also an excellent topic for discussion in physics, as it is how things fall under only the influence of gravity. And so we're going to take a look at that today. Um, It'll finish off our one-dimensional physics motion problems and get us more fully prepared for the test, which should be coming up soon. Okay, so here we go. This is the 16th video. It's on free fall, and let's get going. First, why do things fall? Well, actually, that was, if you've heard of Isaac Newton, I'm sure, that was the topic that he was trying to discover. He says that he was in his orchard, and so he was sitting under a tree, right? So he was sitting here under a tree, and here he is looking up at the sky, and he noticed that there, lo and behold, was the moon. And sometimes, you know, the moon, you can see the moon during the daytime. So that was one of those times that he had a chance to see the moon. And he thought to himself, well, wait a minute. So what is it that keeps the moon in orbit around the Earth? And he says, unlike what the story is that you've actually probably heard from your middle school teachers, that he was occasioned by the fall of an apple. I don't know why, but people have told the story that it fell on his head. And that's not quite the case. He said he just saw it fall, and as a result of seeing it fall to the ground, he thought, well, maybe this gravity thing is the reason for it. And so that launched him into all of his thinking about motion and laws of universal gravitation. So it's kind of cool to think about that that was the impetus for it. Also kind of cool to think about he did it all while he was on vacation from college. So he took a year off because of the Black Plague in London, and was hanging out at his uncle's orchard to try to escape and try to not get the disease, and decided he would just, you know, invent physics. It's good. It's all good. Anyway, so Newton described gravity as a force that causes an acceleration. Why does the apple fall? Well, so the apple, that's not a great drawing, but you get the idea. The apple has a certain amount of mass, okay? And the apple has to be close to the surface of the Earth. And what Newton told us was that the Earth and the apple have an attractive force between them. Now the Earth is massive, so this tiny little apple is going to have very little effect on the Earth. However, because the Earth is so large, its pull is very noticeable on the apple. And so even though there is also a pull upward on the Earth, because it's so big, you don't really notice it. But the apple then falls as a result of the pull that the Earth exerts on it. And we call that gravity. That's why things fall, because they have this gravitation. Now, Einstein said this is a nice idea, and it works to a certain extent, but it's not quite correct. And we'll talk about what he thought later on when we talk about universal gravitation. But for right now, this is a pretty good approximation for us. And this gravity is a force. And forces cause accelerations. And so the apple accelerates downward. That's the gist of this whole thing. Now, on your formula sheet in 2.6, right there, you have our first constant for the year, and that is the acceleration due to gravity, is a little g. There it is, little g right there. It is negative 9.81 meters per second squared. This is the acceleration due to gravity. What does that mean? That means that any object near the surface of the Earth will experience an acceleration towards the Earth that is equivalent to this 9.81 meters per second squared. Every second that an object is allowed to fall, it will fall 9.81 meters per second faster. So that's what that means. So this little g is something that comes up again and again and again in this class. So we want to make sure that you know it. It's the acceleration due to gravity. There it is, right there. Negative 9.81. What the heck does that negative mean? Well, if you recall, when we talked about choosing your set of axes for a vertical problem, typically we select positive as being up and negative as being down. But even more than that, in physics, negative usually means attraction. So wouldn't you agree that the apple and the Earth are attracting each other? It just so happens that the apple can move a little bit easier than the whole Earth can. But they experience an attraction, and so that negative symbol tends to mean attraction. We're going to see that again when we come to other forces that are attractive as well. Okay, so now how do I figure out how fast objects are going to fall right before they hit the ground? So I want to show you an example of using that little g right there. And we'll use an apple again. I'll see if I can draw a better one this time, so no judging. Okay, so let's imagine that we have an apple here, like so, sort of. I don't know. It's about as good as I'm going to get today, apparently. There we go. So we have an apple, and that apple is at a height above the ground of, let's say, 5 meters. And I'll give myself 3 sig figs on that. So it's a height, so I'm going to go ahead and use the h right there. But what that means then is that the object is going to fall when it falls in this direction. And so this is the height, but then that would mean its vertical displacement. And remember, vertical displacement looks like this, right? Delta y, not delta x for my class. So how far is it going to fall? Well, if this is the 0 line, this must be the negative 5 meter line down here. And so the answer for that is that its displacement when it falls will be negative 5.00 meters. Why? Because, and why negative? Because it's falling towards the ground. And we assume that the 0 line is going to be where you start. It doesn't have to be, but it does make a lot of sense if you go ahead and do that. Okay, so you remember that no time formula? Let's see, the no time formula was 2.5, if I recall correctly. So 2.5 said, if I have an object and I don't know the time that it takes to be accelerated, I should still be able to figure out how fast it's going at the end of its motion. And I do that by using that formula v2 squared equals v1 squared plus 2a delta x. Again, this is the acceleration, and this is the change in, this is the displacement. So here's our apple. It's hanging from the tree, and then for reasons we don't know about, it starts to fall. And so the stem breaks, and then it starts to fall to the ground. So my question that I'm trying to ask you here is, right there, how fast is it going? V2 equals what? I don't know. So how can we figure that out? Well, it's pretty straightforward. I can solve this knowing what I know about the situation that I have here. What's the initial speed? Well, hopefully you're thinking, well, it's hanging from a tree, and so its initial speed is going to be 0. Good job, if that's what you were thinking. If you weren't, get on board here. So its initial speed is 0. Its final speed we don't know, as we just said. Its displacement is this delta y, which is negative 5.00 meters. And then the reason it falls is gravity. And so we know we need to have some factor that is related to gravity that's in that formula right there. And if you're already figured it out, awesome. The factor is right there. The acceleration that you're going to use is the acceleration due to gravity, that little g we just talked about. And so if we're going to do the math for this, we're going to solve this problem, this formula, specifically for finding the speed of an object dropped from rest just before it hits the ground. So what I'm going to do is try to solve this for v sub 2, knowing that v sub 1 is 0. So let's take a look at what that would look like. Well, I'm going to take v sub 2, and I'm going to take the square root of that, which means I get rid of the squared sign on this side. But if I square root this side, I have to square root the other side as well. Now I'm not going to write that because I know that that's 0, and 0 squared is 0. So that's going to go away. And what I'm left with is this. V sub 2 is equal to the square root of 2 little g delta y. Delta y, again, is the vertical displacement. Little g is the acceleration due to gravity, or negative 9.81 meters per second squared. So that is actually our next formula, just simplified. I just took that formula and simplified it out. So that's our 2.7, I believe. Yes, 2.7 right there. Excellent. So that's a little bit of a hint for you, a way to shortcut things for you. So let's solve it. Well, v sub 2 is equal to the square root of 2 times 9.81 meters per second squared times, oops, I'm sorry, that's a negative sign right there, times negative 5.0 meters. There we go. Okay. So from a unit standpoint, I'm sorry, that's a little messy. From a unit standpoint, you can see you've got meters times meters divided by second squared, and then you take the square root of that whole thing, you'll end up with just meters per second. So from a unit perspective, we know we did it right. Awesome. Okay, so let's go ahead and solve this here. So I'm going to cheat, sorry, just to make sure I get it right for you guys. So I'm going to multiply 2 times 9.81 times 5, and then I'm going to take the square root of that. And I end up with v sub 2 is equal to 9.9045, etc., etc., etc. meters per second. Okay. Now, let me ask you a question. Obviously, I put in more digits than I need. So my question for you is, how many sig figs should I have? Well, you might think that you need to take into account this little g right here, but little g is a constant, so it does not count for significant figures. Only actual measurements that you make count. And so this is a measurement here, this delta y, negative 5.00 meters per second, meters. So you see that it has 3 sig figs, so our answer can only have 3 sig figs. So I'm going to put the overbar right above the third digit right there. So 9.90 meters per second is how fast it's going to go after it's fallen for 5 meters. Good with me so far? I hope so. Okay, so we're going to do the second little test here. Hopefully this will go a little bit faster. How do I find out how long it takes for a falling object to hit the ground? So now I'm looking for how long it takes. In other words, a time. So let's take the same situation there. And let's take a look at it again here. So I have my apple. Getting pretty good at drawing apples here. Just kidding. Still not great. Looks like a red piece of toast for some reason. So there's my apple. Ooh, that's even worse. Okay. And it is at some distance above the ground. There we go. And so my question for you is, I need to know the time that it takes to fall. And if you recall, just a few minutes ago, we talked about how the displacement between our apple and the ground was delta y, which we said was negative 5.00 meters. There we go. There it is. So that's our time. We're looking for our time. We don't know that. And there we go. That's much better. Pen is acting up a little bit here. So my question for you is, it's hanging from the tree, minding its own business. Then for reasons we don't understand, it starts to fall. So if you're thinking about the problem, you can think, well, hey, I know that the initial speed then has to be 0. And then, of course, there has to be some reason that it falls. And that some reason that it falls is going to be gravity again. So you're going to imagine, you're going to take into account somehow the fact that gravity is at work. And how do we do that? We do that by including the acceleration due to gravity in our situation here, which was little g equals negative 9.81 meters, there we go, per second squared. Excellent. So this is what we know, or what we need. How can we use that to figure out what our answer is? Well, there is another problem here, and we're looking for time, so we have to include time as one of the variables in our formula, which means we can't use the no time formula like we did last time. So we have to go back to our 2.4, there we go, the master equation, and use that. So remember, the master equation looked like this. The displacement is equal to the initial speed, or initial velocity, times the change in time, plus 1/2, to wait for it to catch up here, times the acceleration times the change in time squared. And remember that squared only applies to the change in time right there. Okay, so I need to solve this for time. And I don't know about you, but I don't want to bust out the quadratic formula to be able to do this. I don't remember it. I had to sing it just like you did when I was in high school, but I don't remember it. Quite frankly, I have to look it up every time. So there's like 1 or 2 things in there I can't ever remember. So there's an easier way to think about it, and it really comes down to this. Okay, so if you remember that initial speed is 0, that term goes away, and then this becomes a much easier thing to solve. And so let's go ahead and show you what that would look like. So delta x, which becomes delta y because it's a vertical displacement, is equal to, that goes away because this is 0. 0 times anything is going to be 0, is equal to 1/2. The acceleration, which we're going to use, is g, so hopefully that makes sense. And what we're trying to find here is this delta t, which is squared. There we go. So we've simplified our formula a bit, and we've plugged in things that we know, so we're good to go with that. Now all we need to do is solve this formula for delta t right there. So I'm going to bring this 1/2 to the other side by multiplying both sides by 2. So 2 delta y. And then I'm going to divide both sides by g. And last but not least, I'm going to take the square root of both sides so that this is just delta t. And finally, we are there. That's it. So this is the formula for figuring out how long it takes for something to fall from rest, which, if you see your formula sheet, it is 2.8 on the formula sheet. I try to make your life easier by giving you some shortcuts there. There you go. But you can see where it came from. So let's solve this to be able to figure out how long it takes to fall, this 5 meters right here. So I'm going to go ahead and plug in. So I'll switch my markers again here. Delta t It's having some troubles here, is equal to the square root of 2. Now 2 is a constant, so it's not going to count for our sig figs, times negative 5.00 meters divided by little g, which is negative 9.81 meters per second squared. And it's the square root of all of that stuff, right? There we go. So I'm going to, again, bust out the calculator because I want to make sure to get it right for you guys. So let's see what it looks like. 2 times 5 is 10 divided by 9.81 gives me, oops, hang on a second. 10 divided by 9.10, there we go, divided by 9.81 equals 1.019. Now I'm going to take the square root of all of that because I have to remember that. And I end up with this value right here, 1.009. Boy, pen is really not good today. 6. And because you can see here, we've got meters, and meters are going to cancel out, and seconds squared we're going to be left over with, but we have the square root, which means we only have seconds, which is awesome because time is measured in seconds. Whew. Okay, how many sig figs do we have? This is a constant, it doesn't count. This is a constant, it doesn't count, and we have 3 sig figs there, so our answer is this, 1.01 seconds. So it's almost exactly 1 second to fall 5 meters. And so that's how we do it. And again, these are objects that are in free fall. At any time, did I talk about the fact that they were being under the influence of air resistance? No, I didn't, because air resistance can, for many instances, be neglected because its effects are so small. So it's much easier just to get a pretty good approximation than to have to go through all of the tricky calculus work of figuring out how much air resistance would be involved in dropping something. It makes your life a lot easier. And really, you're not off by very much anyway. So there it is. Okay, sorry this was a little bit longer, but definitely worth it. So you had a couple of examples on there. Thanks for watching. Take a few minutes to fill out the note sheet and the interesting question form. Obviously, the discussion for this one is going to be crucial for making sure that you guys understand what you're doing. This is the end of the second unit, and so you should start to prepare, if you haven't already, for the test for this unit. This is all there is to it. So make sure if you have questions that you definitely ask, because this is the first actual test that we're going to have. It's something that sometimes blindsides people if they're not ready for it. So please make sure that you over-prepare, if possible, to be able to take the test. You'll be much happier as a result if you do well on this first test. And remember, there's only 3 tests in a quarter, so you want to make sure to do well. All right, with that, I'm going to sign off. Good luck to you. Good luck on the test, and have a good day.